In this lecture, we start with our second aspect of stoichiometry, which is on compounds. Remember, stoichiometry is the quantitative relationship between the chemical entities. In our last lectures, we focused on the different entities as reactants and products, but also we can focus on the entities that's in the chemical compounds. Remember, for chemical compounds, we could have molecules versus atoms, compounds versus ions. So we still talk about the different numerical relationship between the two different entities. So we start our discussion focusing on this perspective. So for example, if we have a chemical formula like H2SO4 sulfuric acid, we can say such following statements like 1 mole molecules of H2SO4 contains 2 atoms of hydrogen. Remember, here we talk about atoms. It's not molecule for those elements. 1 molecule for H2SO4 contains 1 atom of sulfur and 4 atoms of oxygen. So here we see 3 statements. Again, in these statements, we see 2 different pieces of information in each statement. So for example, 1 molecule H2SO4 versus 2 atoms of hydrogen. Remember, a statement contains 2 pieces of information should be considered as conversion factor. The same for the next 2 statements as well. So in this way, we can write this relationship, this statement into something similar, but this time we insert unit of moles in these statements. So like 1 mole of H2SO4 contains 2 moles of hydrogen, contains 1 mole of sulfur, and 4 moles of oxygen. Now, we transferred the ratio between the molecules atoms into the moles of different chemical entities, which is what we call as a stoichiometry. As you can see, 1 moles of H2SO4 equals to 2 moles of hydrogen atoms. 1 mole of H2SO4 equals to 1 mole of sulfur, also equals to 4 moles of oxygen. And of course, we can put them all combined so that 1 mole of H2SO4 equals to 1 mole of sulfur equals 2 moles of hydrogen equals to 4 moles of oxygen. All of which is what we call as a stoichiometry, because that's a molar ratio between 2 different entities according to what? According to a formula. So that is very important. So I'd like to emphasize this one more time. Stoichiometry reflects 2 aspects. One, from a balanced chemical equation between the entities we label as reactants and products. The second aspect, we refer the stoichiometry as the relationship between the constituent element in the compound. All right, speaking of the calculation problems, remember at the very beginning of this chapter, we said there's a mass moles number conversions. So for example, we have a mass moles number conversion, and for the first one, so we have molar mass as conversion factor. Between the moles and numbers, we use the definition for moles as conversion factor. All of this are referred to compound. So we use compound as entity to establish this mass moles number conversion. For same reason, we can establish the mass moles number with regard of their constituent elements like A or B. Again, this is 2 parallel solution maps. They do not cross over each other, because we talk about the two different chemical entities. However, we can connect or we can bridge these two parallel solution maps with stoichiometry. So here I just want you guys to realize where this x comes from. X comes from, as you can see, comes from the subscript of this constituent element. Of course, you can also say 1 mole of AXBY equals to Y moles of B if you want to, or if you want to emphasize on the other side, instead of A, it could be the constituent element of B. But nevertheless, I want you guys to realize still this H-shape solution map that's also applied to the compounds with regard to their constituent as elements. Now let's look at a question. The question says tetraphosphorus digoxide is used as a drying agent due to its reaction with water to form phosphoric acid. Now we're asking what is the mass in grams for this amount of molecules of tetraphosphorus digoxide. And the second question asks just how many phosphorus atoms in the sample. Of course, first we need to know what the formula of this so-called tetraphosphorus digoxide. Tetra means 4, deca means 10, so the formula is P4O10. That's easy. So now let's look at the first question. First question says the mass for this amount of P4O10. So remember those procedures we already highlighted in our handout. So we just follow that one more time. So our first step, we record and list every number with the unit entity, which is the complete piece information. So I like to point out here the complete information right here is the number and the entity. So we write down what is given. So we got the 4.65 times 10 to the 22nd P4O10. Since there's no reactions involved here, so we cross out whether there's going to be a reactant in the product because it does not apply. All right, so what is question 1? Question 1 is grams of P4O10. I just want to let you to realize P4O10, P4O10. So same or different entities according to this question. We may answer that question later on in step 3. All right, step 2, we collect the information. We collect the conversion factors. First, there is an anti-balanced chemical equation for us to look at here, so we skip that part. And as for our second step, no density, no concentration, so we skip this step. Step 3, calculate the molar mass if grams or the mass is involved. Remember, the question wants us to figure out how many grams of P4O10, so we need a molar mass of P4O10, which is 284.0 grams of a P4O10 equals to 1 mole of a P4O10. As we move on to the next step, we realize question has a certain number of P4O10, so we have to use the definition for mole. So 1 mole equals to 6.022 times 10 to the 22nd, but here I just want to have those entities attached. So 1 mole of P4O10 equals to 6.022 times 10 to the 23rd P4O10. And here, at the end of this collection of conversion factors, we collect the 2 conversion factors. So one is for molar mass of P4O10, second, definition of a mole in terms of P4O10. Of course, we skip the 5th step because that is for the gas chapter only. Now, step 3, we're asked this question. Are given and these are entities the same? I just want you guys to realize here, this is P4O10 that's desired, P4O10 that is given, they are the same. So the answer is yes. I just want to remind you that's the same entity, right? So this is the same entity, so we're looking for this solution map. So question wants us to figure out the grams from number of molecules. So now we realize we start number of molecules through moles, then to the grams. Okay. So this is the solution map that we're going to use for this question. All right, so with all that being laid out, so our solution map here is from number of P4O10 through moles to get the grams of P4O10. As we carry out the calculation here, so we got the number of P4O10. Okay, remember this conversion factor right here is definition for mole, so we use this conversion factor right here. So 1 mole of P4O10 equals this many of P4O10 molecules. So that we can convert the number of molecules into the mole. And finally apply the molar mass as second conversion factor, we can get the grams. Now let's look at the second question here. How many phosphorus atoms are presented in this sample? And again, from step 1, we collect the information, right? So remember our information given is this many of the P4O10 molecules. Again, there's no reaction, so reactant products of the not apply. And remember, question wants how many phosphorus atoms. I just want to have you guys realize, even though I put them in different color, they are different substances. Okay. What does that indicate? It indicates a stoichiometry calculation problem. All right, so as we move on to the second step, collect the information. So we can pretty much skip the rest of the steps because the only step that is good enough for us to collect information is if numbers of atoms or molecules involved, since they both are given and desired. So we can write our first conversion factor, 1 mole of P4O10 equals to a certain number of P4O10. 6.022 times 10 to the 23rd, so that is, I forgot our number. And remember, numbers of phosphorus atoms also are asked. So 1 mole of phosphorus equals to 6.022 times 10 to the 23rd phosphorus atoms. I'm sorry, I forgot phosphorus right here. So that's phosphorus atom. I'm sorry, this looks ugly, but you know what I mean. All right, so from this step, we collect 2 conversion factors, although they have the same number, 6.022 times 10 to the 23rd, but as you can see, we have 2 different substances. So each substance have its own conversion factor. Again, question number 3, are given desired entities the same? Of course it's not, because one is P4O10, the other one is phosphorus atoms. So first step we pass because it's not the same entity, and we realize it is a stoichiometric question. Since it's a stoichiometric question, so what's the stoichiometry, by the way? Remember, this is about the formula. As we can see, phosphorus is a constituent element in this molecule of P4O10. So subscript becomes to the stoichiometry, which means 1 mole of a P4O10 equals to 4 moles of phosphorus. Again, this is our third conversion factor for this problem. All right, so now if you look at the solution map, so I want you guys to realize we start off P4O10 right here, and the question wants us to figure out just how many phosphorus atoms. We start with the numbers of the molecules. Remember, go to the moles of a phosphorus atom, then to the moles of numbers of phosphorus atom. So remember, numbers to the moles, that's for P4O10, moles to the number, that's for the phosphorus atom. This is exactly what we write it down right here for the solution map. So number of P4O10 to the moles of phosphorus to the number of phosphorus. All right, so let's carry out the solution map by setting up the calculation. We start off 4.65 times 10 to the 22nd P4O10. So get to the moles. Then moles of phosphorus, remember, stoichiometry is a 4 versus 1. And from moles of phosphorus to numbers, again, this is definition of a mole. And calculation leads us 1.86 times 10 to the 23rd phosphorus atoms. That is for this calculation example problem. Well, what is the application of stoichiometry of a formula? In order for us to explain, to understand this concept, okay, its application, we first need to learn or to review what the mass percent is. This is something that we have discussed in our lab weeks ago. Okay. Remember the hydrate salt, okay, it's hydrated salt, copper 2 sulfate, pentahydrate, we heat it up and the water is gone, blue crystal becomes the white powder. So in that experiment, we talked about mass percent. So if you recall, in that discussion, I said there's two definitions of mass percent. We can have mass percent from sample, and we can have mass percent from a formula. So from sample, so it is equals to the mass of element in the sample we measure divided by the total mass of sample we collect times 100%. The same mass percent could be a different formula if we know what the formula of the sample is. So the same mass percent of the element equals to the moles of this element X multiplied by its molar mass divided by the molar mass of the entire compound times 100%. Okay. So how do we know the moles of this element? The subscript, because the subscript indicates the stoichiometry. And if we talk about hydrate, that would be the coefficient in front of a hydrate that we can use as a coefficient multiplied by the molar mass of the hydrate, of course. And if you recall our experiment, well, let's get used to these two definitions of mass percent a little bit before we move on. Okay, so our first question is to calculate the mass percent of nitrogen in a compound called ammonium nitrate. And second question, how many grams of nitrogen are in this many kilograms of ammonium nitrate? First of all, we need to know what ammonium nitrate is. Ammonium, NH4, nitrate, NO3. All right, since we talk about the mass percent, so we just put this 2 nitrogen. So this is 1 nitrogen here, and this is another nitrogen. So we put 2 nitrogen dot together to rewrite this formula as N2H4O3. All right, so this is the formula. Because we know what the formula is, so we can use the second definition of this mass percent based on formula, right? So figure out what the mass percent of nitrogen is. Remember, the subscripts becomes to the coefficient of each element. So subscript nitrogen is 2, so with 2 times nitrogen divided by, this is what the entire formula is, constitutes 2 nitrogen, 4 hydrogen, and 3 oxygen. And we're going to replace those symbols, chemical symbols, with their molar masses. So 14 for nitrogen, 1.01 for hydrogen, 16 for oxygen. So we figure out it's a 35.00%. All right, so this is our second definition of mass percent, if we know the formula. So now that we have mass percent, we can use the first definition to calculate just how much of a nitrogen we have in that amount of sample, which is a 35.8 kilograms. All right, so if you remember, 35.00% equals 2 grams of nitrogen divided by 35.8 kilograms of ammonium nitrate. And of course, okay, and that is going to be multiplied by 100%. Okay. However, we realize grams and kilograms cannot be canceled, so that is why we need to convert this in a little bit, right? So grams and kilograms can cancel after this conversion factor was introduced, so we realized we can carry out the calculation to figure out what just a grams of nitrogen is. So calculation shows us it's going to be 1.25 times 10 to the 4th grams of nitrogen. Okay, so from this question, we understand there are two definitions of mass percent, one from sample, one from the formula. In our example problem, we understand if we have a formula, so we can use mass percent of formula to solve for the mass of the element if we know the total mass of sample. But in reality, it is quite common that we send out our sample with the mass known, and they can tell us how much of the element in that sample, which means we know the mass percent of the element. Well, remember, the same mass percent can be represented by this formula. That means if we can go backwards by knowing the mass percent of the element, and with this formula, we know the molar mass of the element. If we know the formula, we could know the molar mass of a compound. All right, speaking of formula, here is the subscript. So, can we solve the subscript of this element? If we can solve the subscript of the one element and another, which means if we can solve the subscript of all constituent elements, we should be able to know what the formula is. So with that in mind, here comes our second application. And there's a few concepts I'd like you guys to pick up from chapter 2, chemical formulas. So here we're going to focus on empirical formula and the molecular formula. Empirical formula, as we understand, is the simplest whole number ratio of the different substances or the constituent elements. It has a very little chemical information. Remember CH. There's no such compound with the formula of CH, C1H1. But that formula is good for all the ionic compounds like NaCl, right? So 1 sodium plus 1 Cl minus. So we also call such empirical formula for ionic compound as formula unit. On the other hand, the molecular formula is the actual number of atoms of each element in a molecular compound. That means the same empirical formula could lead very different molecular formulas. If you recall in chapter 2, as we discussed, if we multiply CH by 2, so we can have C2H2. If we multiply the same empirical formula CH by 6, we can have C6H6, the two very different organic compounds. So here, what we are going to do is we move one step forward. Okay. So from the mass data, for example, mass percent, we should be able to get the empirical formula, and with the help of additional information, we should be able to figure out a molecular formula once we know what the N is. For example, multiply by 2 on CH or multiply by 6 on CH. So the difference between the empirical formula and the molecular formula is what this N is, or we call the multiplier. So here's the procedures in determining the formulas, empirical formula as well as molecular formula. So it has 3 parts. As the first part, we check the sum of mass percent, make sure it's 100%. Then we simply assume that's 100 grams of sample, so we convert that percent into the mass, then to the moles. Okay. So first we need to get the mass, then the moles. Okay. And of course, as you will see in your homework assignment, so sometimes we have a mass of each element. So if we do, we simply convert the mass into the moles of each element. So basically, we try to convert mass data into the moles. So that is only 1/3 of this process. However, it is this process that is most important in this procedure to determine empirical formula, because we need to follow the step one by one without any alternation. So first, we're going to write a pseudo formula. Pseudo formula means we have a formula. The only difference here is instead of a whole number as a subscript, we use fractions. Why fractions? Because sometimes if we have moles, so we use number for moles here. Okay, so the moles as the fraction for that formula. All right, so once we have the pseudo formula, our next step is divide the formula by the smallest subscripts we can find in that pseudo formula. Okay, by doing this, we can have at least the subscript of one element as 1. That is important. Remember, for formula, the subscript must be a whole number. Then we're going to find a multiplier to multiply all the subscripts in order to remove the fraction. So here comes the rounding rule. Rounding rule is a very specific. Okay. So if we can only round up or round down once the number, okay, the subscript, okay, so the fraction to the whole number if they're within plus minus 0.05. It's not a 0.5, 0.05. Very small range. All right, so after we round it up or round it down, so we can have an empirical formula. So once we have an empirical formula, we can calculate the molar mass of this empirical formula. And we can calculate so that we can have a molar mass of empirical formula. So in order for us to get this multiplier n here, so we divide the molar mass of formula that is provided by the question usually, divided by the molar mass of this empirical formula. So once we know the n, molecular formula is equal to empirical formula multiplied by n. All right, before we practice, I'd like you guys to understand what is the conversion in order to have the fractions to the whole number. Okay. So these are the common fractions we will see here. Okay. So what happens if we have some number very close to the 0.33 or 0.32 to 0.34? What multiplier should we apply? If you realize 0.33 is 1/3. Since it's 1/3, so all we have to do is multiply by 3. And what about 0.67? 0.67 is, you got it, that's 2/3. So the same multiplier apply to 0.67. So instead of getting 1, now we get 2. 0.25. 25 cents is called a quarter of a dollar, so 0.25 means 1/4. 0.5, you may know it, it's 1/2. What about 0.75? Yes, 3/4. So as you can see, for 0.25, 0.75, they have the same multiplier. 0.20 means 1/5. So the multiplier is 5 for 0.1, so that's 10. So these are the common conversions or the common multipliers we can apply so that we can convert the fractions into the whole number. All right, so I want you guys to memorize this 0.67 a little bit longer. Remember, the multiplier for 0.67 is 3 because we're going to use it in our example. All right, so in this example, okay, so we have some compound. This is a carcinogen, so that's compound can cause cancer. So this compound is called a benzoyl alpha pyrene. Okay, so complicated ones. But we know the molar mass. The molar mass is 252.30 grams per mole. This compound can be found in coal dust, cigarette smoke, and charcoal grill meat. Usually it's overburned, so you can see the charcoal on the surface of the meat. Okay, so if we send out a sample to analysis, so it shows 95.21% of carbon and 4.79% of hydrogen in mass. Question wants us to figure out what the molecular formula of this compound. All right, for this type of calculation problem, all we have to do is to follow the procedures that we laid out a couple slides before. So remember, there's 3 big parts. The first part, check the cell mass percent to be 100, convert the mass percent into the mass and moles, right? So first step, we multiply 95.21 with the 4.79. Okay, so that's 100. Okay, so this condition is checked. So we assume that's 100 grams of the sample. So that means we got 95.21 grams of carbon converted to the moles by divided by its molar mass. Remember, that is elemental carbon. So we just simply copy down atomic mass as molar mass of this element from the periodic table. So that's 7.928 moles of carbon. Speaking of hydrogen, okay, so divided by 1.01. And I like to point out here, okay, for the calculation, at least 3 sig figs. It's very important because if you keep 2 sig figs, you might wind up a totally wrong formula. Okay, so that's gonna cost you a lot of credit, even though you carry out the rest of the calculation right. So make sure that 3 sig figs at least. All right, so once we figure out the moles of each element, so we're gonna write up the pseudo formula. So here I want you guys to notice just how we write the formula. Carbon, and we have the subscript used from the number of moles of each element. So 7.928, hydrogen 4.74. All right, so we understand that this is not going to be a formula because formula cannot have fractions. So that's what we call pseudo formula. And we cannot round. The reason for that is either the subscript is not fit for rounding. Okay, and remember, we have to carry out the step. First, get the pseudo formula. Second, we divide the entire formula by the smallest subscript before we even think about rounding. So after we divide this formula by the smallest subscript, 4.74, we wound up with 1.67 hydrogen 1. Again, we cannot run because we got one more step to go. What's the step? We convert that fraction into the whole number. That is why 3 sig figs is a must, because if you want up 1.7, you're not going to be able to get the correct formula, no matter how hard you try it. So remember, 3 sig figs at least in order for you to carry out the calculation. All right, 1.67. The fraction is 0.67. Remember what the multiply for 0.67? 3, right? So that means we need to multiply entire formula by 3. 1 times 3, 3. 1.67 times 3, 5.01. Now, 0.01 is within the range for us to round it down. So empirical formula, C5H3. So that is our empirical formula. All right, it is not an empirical formula that question wants. Question wants the molecular formula. So we carry out our third step. Okay, it's the third part. So we calculate the molar mass of this empirical formula. So what is the molar mass of the empirical formula? 5 carbon, 3 hydrogen. So 5 times 12 plus 3 times 1.0. So we got a 63.08. Remember, 3 sig figs at least. Remember, the molecular mass, or the molar mass of this entire compound is 252.30. So 252.30 divided by the molar mass from this empirical formula. So usually it should give us a very good number that's either whole number or very close to the whole number. So we can round it up or round it down so that we can have the multiple. So the multiple is a 4.00. So we're going to multiply 4 to this formula. So we got a carbon 20, hydrogen 12. This is the molecular formula. And this is what we call a structural formula. So that indicates just how many carbon. There are 20 carbon and 12 hydrogen, how they are going to be arranged. So this compound is called a benzo alpha primary. All right, now we step into the last major concept of this chapter, solution. Solution, as we discussed from chapter 1, it is a homogeneous mixture of 2 or more substances. And here, I'd like to introduce 2 more terminologies regarding the solution. First, solute. Solute, remember, the solution contains 2 or more substances, so depending on the amount. So we call solute for the minor components. So here it is a plural form, so that means we could have more than one solute. And for solvent, it is a major component, that means a large amount. So for example, if you open up a soda, okay, so you understand we have carbon dioxide, okay, we maybe have some sugar or sweetener, and also something that gives the color of the soda. So all of this, because they are very small in numbers or in amount, so we call them solutes. So we could have multiple solutes, but usually we consider there's only one solvent, of course. The water is the major component in the soda, so we consider water as a solvent. Solution is homogeneous because they're mixed in very tiny scale, like atom, ion, and molecular. So that's why we cannot see it from our eyes. So it's clear and transparent. And aqueous solution, as we already know, so we use water as a solvent here. Well, it is not the definition of a solution that we're interested in here. It is just how we can calculate the amount of a solute in the solution that we are interested in. Because for the reaction, to dissolve our reactants as a solute in the solution, remember, we mix 2 solutions so that we can have the reaction going. So how do we know the amount of a solute in the solution? So here comes the concentration. Concentration is the amount of a solute dissolved in a certain number or certain amount of solvent or solution. So that means we could have various definitions of concentration. So this is going to be the first major calculation we're going to see in the Chem 2 class. 5 different units of concentration. One of the units we're going to discuss today here is molarity. So it's capitalized M to represent molarity. Definition, moles of a solute per liter of a solution. In mass, moles of a solute divided by the liters of solution. This is what we call molarity. As its unit, we call it molar, or M, capitalized M. Has to be, because we cannot use a small case m. It means something else. But I want you guys to use moles per liter instead. Why moles per liter? Because it has 2 different units. What does that mean? Conversion factor. Okay, so as we realize, molarity can be used as a conversion factor, so that indicates just how many moles of solute in 1 liter of solution. And we realize we have 2 different units, 2 different substances, because solute could be the pure substance, solution definitely is a mixture. So we talk about 2 different substances. And what does that tell us solution map-wise? So we can have concentration here as the conversion factor connects moles of solute with liters of solution. Remember, we got number, moles, and mass. Here's the moles, here's the moles. So we can combine these 2 solution map in one. So we have mass, mole, number, volume for the same substance. So here, concentration here used as a conversion factor to convert liters or the volume of solution to the moles, vice versa. All right, let's look at our next example. Here, question wants us to figure out the concentration in capitalized M if a 1.35 liters of sucrose, table sugar of course, solutions contain 135 grams of solute. All right, so let's lay out what we know. We know (135 grams of solute. What's a solute here? Right? So that is 135 grams of solute. And what else do we know? We have 1.35 liters of sucrose. So that's 2 pieces of complete information. And the question wants us to solve M. Does anybody recall what the M is? You got it. Moles per liter. Why do we have to use moles per liter? Because with the moles per liter, we will know what we're going to do first. So let's think about it. Remember, capitalized M means moles per liter. If we put everything together for this moles per liter, that should be moles of solute divided by certain liters of solution. Do we know the certain liters? Yes, we do. It's 1.35 liters. So before we can get M, we should get moles. So all we have to do is solve for moles of solute here. All right. Remember those templates that I give you over and over? So we try that again. So record the complete information. So we got 135 grams. And that's not the reaction we are talking about, so it doesn't apply. And question wants us to solve for moles, right? Because remember, once we know the moles, we can get molarity. So I just want to point out, when we make up a plan, we can have very different desired units and entity from the question. All right, next step, we collect the rest of the conversion factors. There's no reactions to talk about, so we pass that. No density. Concentration is something we want, right? Question wants, but it does not provide, so we pass that. All right, so remember we got the grams. We got the grams of this substance. So grams is given. So molar mass of the sucrose is 342.34 grams per mole. And so we write it up. So 342.34 grams of sucrose equals to 1 mole of sucrose. All right, by the way, that molar mass is our first conversion factor. So as we move on, remember there's no number of atoms or molecules involved in the question. We pass that. Again, STP is something we talk about in gas, so we pass that. All right, so now question. Are we talking about the same entity? Yes, we do, right? Because we need to get from grams to get moles, the same entity. So it's a yes. So once it's a yes, so we now know, we know the grams. Question wants to get the moles right here. So that's very simple, just one step of conversion right here. All right, so solution map, simple, one step conversion from grams to the moles. Carry out, so we figure out that's a 0.394 moles of the substance. And moles divided by liter, so that's what the molarity is. So that's a 0.292 molar, M-O-L-A-R, molar sucrose solution. All right, our last example problem before we wrap up this chapter. This is something that's very similar to our titration in our experiment in our lab. So how much milliliter of a solution of sodium carbonate Na2CO3 are necessary to completely react with the 27.2 milliliters of certain concentration of HNO3 according to this reaction. As a reminder, always check for this equation for whether it is balanced. Because as you can see, it is not balanced. You got 1 sodium here and 2 sodium there. So always check the equation to see whether it is balanced. Sometimes, if you miss that part, that thing is going to get you in trouble. All right, we're going to follow that template one more time. So we record, we write things down. So here, I just want to remind you, we got a lot of things here, a lot of piece of information. So first, this. Second, this. Third, this. And remember, in this chapter, not only we have number and units, we also need to attach the entities. So for 0.112, not only we put M of sodium carbonate, and also I want you guys to pay attention. We need to rewrite M into this, moles per liter. Why moles per liter? Because moles per liter is what we call the conversion factor. 2 units in a slash. We're going to deal with whether there's going to be a reactant product later because we have the reaction right here. All right, 27.2 milliliters of the same solution, also nitric acid, so nitric acid solution. And the concentration of the nitric acid solution is moles per liter. And the question wants us to figure out the milliliters of a sodium carbonate. All right, so when we organize information, we need to do that very carefully because sometimes they could have same unit, but very different substances. We need to know which one is which. All right, are these two reactants? both or one reactant or one product. As we check out this reaction right here, so nitric acid, reactant, sodium carbonate, reactant. So we realize, okay, we know one reactant with the amount. Question wants us to figure out the second reactant. Two different substances, meaning stoichiometry. One reactant no, meaning it is a not limiting reactant problem. So this is as much information we can get by labeling the reactants and products for the information that we extract from the question. Second step, we collect conversion factors. First, remember, we need a balance on chemical equation. So by putting 2 in front of a nitric acid, we have this equation balanced. Okay. And stoichiometry, remember, we only have 2 substances we are interested in the question, sodium carbonate and nitric acid. According to here, so this is 2 in front of nitric acid, that means it's 2 moles of nitric acid for 1 mole of sodium carbonate. Okay, because that's 1 mole of sodium carbonate. And of course, this is our first conversion factor we can get from a balanced chemical equation. As for second, okay, density, we do not have density, but we do have a concentrations. 2 concentrations, right? Moles per liter. So we rewrite this moles per liter by break this moles per liter into moles on one side, liters on the other. It is very important for us to learn how to break up a certain unit. Okay. All right, so that is the concentration for sodium carbonate and 1.35 moles for 1 liters of nitric acid. So we just had 2 more conversion factors from concentration. Question does not have grams involved, so we pass number 3, number 4, and number 5, okay, because we cannot collect any more conversion factors from the question. So we have 3 conversion factors. Nitric acid is not sodium carbonate, that is for sure, so that's a stoichiometry problem. And also, it is quite obvious we are given an equation, so most likely it is going to be a stoichiometric question. All right, so remember, question wants to figure out, if I'm not mistaken, the milliliters of sodium carbonate. Okay, so where do we start? Remember, we know the milliliters of nitric acid, right? So you may ask, what happened to the molarity? Remember, molarity is certain moles equals to what? Liter. Moles, liter. So molarity right here is used as conversion factor. So what do we start? We start milliliter to liters, liters to the mole, moles to the moles. Now, we have a different substance, that's sodium carbonate. So moles of sodium carbonate to the liters of sodium carbonate. Now what? Milliliters of sodium carbonate. So, like I said, this is a solution map for pretty much all the calculation problem involving stoichiometry. Okay, it does not represent exactly this solution map, but it provides essential solution map for whatever the problem that is. So for example, in ours, so what we need here is we extend liters to the milliliters on both sides. This is all we need. All right, so we start from liters of nitric acid solution to the moles of sodium carbonate, back to the liter of sodium carbonate. And of course, Remember, we got 2 more steps, convert the milliliters to liters and liters to the milliliters back. Okay, so what's the conversion factor between milliliters to liters? Of course, this one for both arrows. Okay, so that's good for this arrow, and this is also good for this arrow. Okay. All right, so we have 1, 2, 3, 4, 5 steps of conversion. Okay. So that is what we call a solution map for this question, and we're going to carry out this solution map. All right, so let's do 2 conversions in the first line. So milliliters to liters, liters to moles, excuse me. Then next step, that would be this arrow. So stoichiometry, we convert the moles of nitric acid to the moles of sodium carbonate. And the last step would be the conversion in the second row here. So moles to the liters to the milliliters. We have 16.4 milliliters of sodium carbonate solution. That ends this chapter 4. As you can see, chapter 4 is the huge chapter. Okay, so in this chapter, we talk about the unit analysis. We talk about the stoichiometry. And with stoichiometry, we use the 2 basic concepts, definition of a mole and the molar mass as a conversion factor. And on top of stoichiometry, we discussed limiting reactant. If a question is limiting reactant, it is definitely a stoichiometric question. And stoichiometry has 2 parts, right? So first part is based on the balanced chemical equation, and also stoichiometry can be represented by the subscripts of a formula. The application with the help of mass percent of the stoichiometry can be used to solve for formulas. And finally, concentration. Concentration is usually be used as a conversion factor for us to solve the problem. But don't forget, also concentration, how to get a concentration is another type of calculation problem. Okay, so that's it for this part of lecture. I hope you guys enjoy it. Okay, it is very complicated. And of course, there are going to be a lot of homework or a lot of practice for you guys to do. So we got a pretty heavy week ahead of us. So good luck, and I'll see you guys next week.